So in this video, we're going to introduce some of the issues that we run into when we solve equations that have rational exponents. So we're going to have equations that will be of the form x to the m over n, where m and n are integers. That's what makes this a rational number. So this is a rational or ratio exponent. So we're going to have x to the m over n equals stuff, and we're going to need to solve equations of this form. So what we want to do is address some of the subtleties that arise that are dependent on whether m, the number in the numerator position on the rational exponent, is an even number versus what happens when it is an odd number. So let's look at a simple equation involving a rational exponent. Let's say we have x to the fourth equals 16 versus looking at x to the third power equals 8. And in this case, this is a rational equation in the sense that 4 is a rational number. I can write it as 4 over 1. 3 is a rational number because it can be written as 3 over 1. And n down here can be anything, to be a rational exponent, n can be any integer we want it to be other than 0 because we can't divide by 0. So the simplest case is just to look at the case where the rational number happens to be an integer. And what we want to think about is what is this asking us to do? Well, this is asking us to find a number x so that when we raise that number to the fourth power or multiply it by itself 4 times, we get a 16. And 2 is certainly a number that fits the bill because 2 times 2 times 2 times 2 is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 is a solution to this equation. However, it's also the case that negative 2 is a solution to this equation because negative 2 times negative 2 is 4. 4 times negative 2 is negative 8. And negative 8 times negative 2 is also positive 16. So there's two numbers, 2 and the opposite of 2, or a positive real number and its opposite, either of which when raised to an even power 4 will generate an output of 16. So here's the process for solving these equations. Usually you raise this side to the reciprocal of the exponent that you see. So in this case the exponent is 4 over 1, so we raise it to the 1/4 power, and we do that to both sides. The reason we raise it to the 1/4 power is going back to our exponent rules. If we have x to the a to the b, when we raise one exponent to the other, we just get the product of the exponents, a times b. And when we multiply a number times its reciprocal, 4 over 1 times 1 over 4, that equals 1. You just get x to the first or x. So it breaks the x out. But when we take the fourth root of 16, it's going to be a 2 by definition. So what we need to do is add a plus or minus in front, indicating that not only will 2, which is the fourth root of 16, not only will 2 generate 16 when raised to the fourth power, but negative 2 will also generate 16 when raised to the fourth power. So in general, in the case where we have an even numerator on a rational exponent, we're always going to get 2 answers. We always wind up having to put, as soon as we do each side to the 1/4 power, we have to put a plus or minus immediately. And that's going to be for any even numerator, because you put any even number up here. If you raise a negative number to an even power, a negative number raised to an even power is always going to generate a positive result. So that's the first thing we want to recognize. When we are raising x to the third power, which is an odd exponent, the same thing doesn't happen. So this is saying what number, when you cube it or raise it to the third power, will generate an 8. Well, 2 certainly works because 2 times 2 is 4, times 2 is 8. There's 3 copies of 2 being multiplied to give 8. But if you try to do negative 2, it's not going to work because negative 2 times negative 2 is 4, times negative 2 is negative 8. So negative 2 doesn't work. So when we do the solution process, when the numerator is an odd number, we're still going to raise it to the reciprocal because 3 times a third is 1x. But when we raise the right-hand side to the 1/3 power to cancel out that 3 over here, we're just going to get a 2. Negative 2 isn't a solution. So when you're working with equations that have rational exponents, kind of job one, the first thing you do is you look at the numerator of the rational exponent and you say, is it even or is it odd? If it's even, you know that you're going to get a plus or minus in your solution process. If it's odd, you know that you will not get a plus or minus in the solution process. So that's the first subtlety that occurs when we do these types of equations. The second thing that we have to deal with is thinking about when can the algebraic expression raise to a power, when can it be negative? So for example, if I do x to the fourth, we had it equal to 16 on the previous slide, and we had x cubed equaling 8. Well, what happens if we put a negative sign on those two numbers? Do we get a solution that's a real number or not? That's a big question to ask. So we can say, well, what are the candidates? Well, we know 2 times 2 times 2 times 2 is going to be positive 16, which isn't negative 16. So we know that the real number 2 isn't an answer, but we also know that if we multiply negative 2 times itself 4 times, we're going to get a positive 16. So it turns out that if we take x and raise it to an even power, the fact that we have an even power here is always going to generate a positive output. So if we set x to the even power equal to a negative real number, we don't get a solution that's real. We would get a complex number result. So if we're restricting our answers to the real numbers, the idea here would be to say that, well, there is no real number, so that when I raise it to the fourth power, I get negative 16. Therefore, the solution is the empty set. There is no x in the real numbers that works. Whereas if the power is odd, it will work, because when I raise a negative number, say negative 2 times negative 2 times negative 2, when I raise, there's 3 copies of it, right? Says multiply the number by itself 3 times. Well, the product of 3 negative numbers is a negative number. So I can get a solution out of this. So this one I could solve. I could say, hey, raise it to the 1/3 power to get x by itself. A third times 3 is 1. X to the first is x. And raise the other side to the 1/3 power as well, which is going to generate the negative 2, the number that when I multiply it by itself 3 times gives me negative 8. So that's the other subtlety. We wind up needing to pay attention to the numerator of the rational exponents. And it's kind of summarized here on this slide. And I should have changed that to greater than or equal. But you're going to look, the first thing you do, you have an equation involving a rational exponent that you need to solve. Here's the rational exponent, m divided by n. M and n are integers. N can't be 0, of course. You look at the numerator. You say, is it odd? If it's odd, there's only going to be one answer, so we don't need to put a plus or minus. And if it's odd, it's okay if v is a negative number, so v can be any real number you wish it to be. However, if m is even, what we saw in the previous slide is 1, we can't raise a number to an even power and get a negative output. So v needs to be greater than or equal to 0. It can't be a negative number. That's the first thing that we need to realize. And 2, because we're raising it to an even power, we're going to get the positive number that works, but we're also going to get the opposite of that number working as well. So we have to, in the solution process, when we raise both sides to the n over m power to get our exponent of 1, multiplying by the reciprocal, we need to put the plus or minus right away.